Okay, here we are now in section 7.3. This is all about equations that have fractions and decimals in them, and some techniques we can use to clear those fractions out of there. Okay, now example 1, part A on page 336. We've seen before, okay, and we've solved a problem like this before. 4d over 3 equals 12, okay? Now, that's a d there. Recall when we have a fraction, okay? 4d over 3 and 4/3 d are both the same. Two different ways to write the same thing. Okay, and what did we do? Let's solve it the way we know. We're going to multiply by the reciprocal on both sides. Okay, so we might want to slap a 1 underneath that 12 so it looks like a fraction times a fraction. What do we get over here? 12d over 12 equals 36 over 4. Okay, the 12's cancel, and then we simply get d equals 9. Okay, all good. Let's do it again. But this time I want to employ the fraction technique that we're going to use, because when these things get more complicated, we can't simply multiply by a reciprocal anymore. Alright, so what we want to do is we want to look at all denominators. Now we only have one denominator, but look at them all and identify what the common denominator would be. So in our case, it's a 3. And we want to multiply through the entire problem, numerator only, by that 3. So if we want to slap denominators under all this of 1, that's fine. Numerator only. 12d over 3 equals 36. Okay? Now, it doesn't look like we simplified anything. Okay, we started with 4d over 3 equals 12, and now we have 12d over 3 equals 36. It doesn't look any better at all. But it is, because this fraction now divides away nicely. So we're really looking at 4d equals 36, and then we divide by 4 on both sides, and we get d equals 9. Okay? Same answer that we got by simply multiplying through by the reciprocal. We really did the same thing. We just did it in 2 steps instead of 1. We multiplied through by 3, and then we divided through by 4. Like I said, when these problems get a little more involved, we're not just going to be able to simply get away with multiplying through by the reciprocal anymore. Alright, that one we could have, so that's why I chose to do it both ways. If we look at part B, let me just come over here where I've got a little more room. 2x plus 3/4 equals 1. Now, our technique has always been so far, okay, we need to subtract 3/4 from both sides, right? So I'm going to stop right after I do this, because this is not the way I want to do it. Because now I'm stuck with that problem of taking 1 minus 3/4. Okay, so I'd have to give the 1 a denominator, and then I'd have to call it 4 over 4 minus 3 over 4. Not the end of the world, okay? But there's a way to kind of clear the fractions away and not have to do so much fraction work. So let me rewrite the problem, and let's do it that way. Identify your common denominator of all denominators involved. Again, we only have 1, so it's a 4. Multiply through the entire problem by 4, okay? Numerators only, okay? Again, if you want to put a 1 underneath there, if that helps, do it. 4 times 2x becomes 8x, and 4 times 3/4, you can see ultimately those 4's are going to cancel, but I won't do that quite yet. It's going to be 12 over 4. 4 times 3 is 12, numerator only. We had a denominator of 4. Now that side becomes 4. So we really have 8x plus 3 equals 4. Now we're down to the kind of the classic linear equation we've been dealing with here this chapter. Subtract 3 from both sides. I'll get 8x equals 1. Divide by 8. Divide by 8. I still get a fractional answer, but other than that, I didn't have to deal with fractions too much. Okay, and that's kind of the beauty of this technique. As we clear the fractions out of there, we don't have to deal with them very much. Okay? All right. Let's check out example 2 on page 337. Example 2 says 10 divided by x. Now this presents an interesting extra dilemma for us here. Whenever we have a denominator of x, we have to be careful, because in the world of fractions, you're never allowed to have 0 as a denominator, right? Never. So because I have x down there, I cannot let x be 0. So that's like a little exclusion, a little restriction, a little caveat, a little baggage that goes along with this whole problem. Whatever I do, I cannot allow x to be 0. So in the course of solving this equation, if I do all my hard work and I get for the answer x equals 0, I must reject that answer. It's not allowed. Okay, so this is, again, a little extra baggage that just follows this problem around. We can't let x be 0, because if x were 0, I would have a denominator of 0. Not allowed. Okay? Otherwise, let's look at our technique here. I want to clear this fraction out by multiplying through by the common denominator, numerators only. So if I want to put a denominator of 100, I can do that. Okay? So that becomes 10x divided by x equals 2x. And you can see my x's are going to cancel. So I'm just going to have 10 equals 2x divided by 2. Divided by 2, I'm going to get x equals 5, okay? Perfectly fine, safe, legitimate answer. It's not an exclusion. I don't have to worry about it. It's a good answer, okay? Again, we can always check these answers by plugging the calculated answer back in the original problem, and I have to get a true statement. If I don't, something's wrong, okay? Now, let's say we didn't make any mistakes and we calculated x equals 0, we would have to reject that solution. That's called an extraneous solution. If you look at the very bottom of 37, there's a little yellow box there. Roots is the word. The word root, the word solution, when you get into more advanced math, even the word 0, solve, all of those are the same thing. I'm looking for the solutions to an equation. Well, solve is the process of finding solutions, but the roots of an equation, the zeros of an equation, and the solutions of an equation, those are all kind of interchangeable words. So at the very bottom of 337, it talks about extraneous roots. That's if you find an answer that otherwise looks good, but you must reject it because it's not going to be allowed. Okay, example 3 on the next page. Very similar to this one. 0 divided by x equals 5. Okay? Again, I've got a denominator of x. So I cannot allow x to be 0, because if x were 0, I would have a denominator of 0, and that's not allowed. Okay? So let's otherwise continue the problem. I'm going to multiply both sides by that common denominator of x. So now I've got 0 times x divided by x equals 5. You can see the x's cancel. Equals 5x on the right-hand side. Something wasn't making sense. Now it does. These x's cancel, and I just have 0 equals 5x. Divide by 5, divide by 5. 0 divided by 5, that is allowed. That gives me a nice pretty 0. So my solution here that I've calculated is that x equals 0. Okay, and normally that's a perfectly fine answer. Don't ever be afraid of 0 as an answer, right? 0 is a number like any other number. It's kind of special. It's right in the middle of the number line, but it's a perfectly valid solution to any problem. However, in this case, we had a restriction that x is not allowed to be 0. So we must reject that, and we say there's no solution. Okay? Throw it out the window. No good. It's an extraneous solution. Not allowed. Okay. Let's look at example 4. It also has a denominator involving a variable. Now we're switching to the letter Q. You know, we want to hip it up here once in a while with a new letter. Example 4 on page 338. So we've got 12 divided by Q plus 6 equals 1. Okay, now I need to figure out is there any value of q that might give me a 0 in my denominator? Okay, now the quick knee-jerk would be, well, you can't, q is not allowed to be 0, because that's what I did on the last two problems. X is not allowed to be 0, X is not allowed to be 0, so my reflex would be to say q is not allowed to be 0. But that's not correct, because if q was 0, I would still have a 6 down here, and that would be fine. 12 divided by 6 would be fine. So 0 is not a problem in this case, but what is a problem? Well, if you ever struggle to figure out what the problem is, just grab that denominator off to the side and set it equal to 0. Solve your own little equation over here and say, okay, what's going to cause you to be 0, denominator? Oh yeah, if q is negative 6, then my denominator is 0, right? You can see it right here. Negative 6 plus 6 would give me a 0. So that's a restriction. That's an exclusion, okay? So q is not allowed to be 0. Off limits. If I get, or not, I'm sorry, not 0, negative 6. Q is not allowed to be negative 6. If we go through all our gyrations here and we get negative 6 for the answer for q, we must reject it. Okay? Otherwise, let's solve. I'm going to rewrite it just to give myself a little more room. I got a little more complicated creature down there in that denominator now, but that is my common denominator, that q plus 6. So I'm going to multiply by a q plus 6 up top here. Okay? Put it under over 1 if that makes me feel better. Q plus 6 over 1. 1 over 1. Okay? I need to multiply through by that. Okay, now, we know how to do the distributive property. And we're kind of tempted maybe to take this 12 and distribute it across, and ultimately that's what we would do. But I don't want to physically do that, and I'll show you why in a second. I'm just going to write it next to each other. Q plus 6 times 12 over q plus 6. That's the left side of my equation. Now on the right side I would have to distribute, except I'm only distributing a 1. So it's q plus 6. When we have a matching numerator and a factor and a denominator here, this is a multiplication process. These are factors. And when you have matching factors, you can cancel those factors right out of there, just like that. Okay, so the q plus 6 in the numerator and the q plus 6 in the denominator cancel right out of there. Okay, I could only do that with a multiplication sign there. If that were plus 12 or minus 12, I can't do that. But when it's a multiplied, I can, if I have an exact match here. So really the only thing left on the left-hand side of the problem is a 12. 12 plus 6. I'm going to subtract 6 from both sides, and I'm going to get q equals 6 as my calculated answer, but I have to go back and double check if it's allowed. Well, is it allowed? Yeah, it is, because only negative 6 would be trouble. So positive 6 is just fine. So q equals 6 is allowed. It's good to go. Okay? Alrighty, let me see what lies ahead to decide if I should pause or not. Let's do one more. Alright, example 5 is where we really have some fractions cooking now. Okay, here's the beauty of this technique of clearing out the fractions. Example 5, page 339. Negative 1/4 x equals 9 minus 2/3 x. So I have multiple denominators at work here. Okay? The technique is going to be find the common denominator of all these different denominators. Okay? The least lowest common denominator would be preferred. Okay? Well, I've got a 4 and a 3. We hopefully know what the least common denominator of a 4 and a 3 is. It would be a 12, right? So I'm going to multiply through the entire equation by 12. Again, numerators only. I'll put a 1 under it just so I don't forget. So what's this going to be? It's going to be a negative 12 over 4x equals, I got to take 12 times 9, what's that going to be? 108 minus 24 over 3 times x. Okay, are we all good there? All right. Now look, what happens? All the fractions divide away. A negative 12 divided by 4 is just a negative 3x equals 108 minus, that divides away nicely into an 8x. Alright, so now I'm down to a relatively easy equation. I have x's on both sides, but I only have a constant on the right, so I need to put my x's on the left. So I'm going to add 8x to both sides. That's going to give me a 5x equals 108. I'm going to divide by 5 on both sides, and I'm going to get x equals, what does 108 divided by 5 equal? Well, I could turn it into a decimal, or I could, what can I do to simplify that? I really can't do anything to simplify that. 108 divided by 5, right? Because there's no 5 hidden inside of a 108. 5 is prime. So, I mean, that's a fair answer there. We'll just leave it as 108 over 5. Alright, that's our solution. Alright, we'll do a few examples in the next video, kind of practical examples using this same technique. And then later we'll talk about decimal problems.